So let's talk about a situation where we go from 0 meters a second, and let's go to 30 meters a second. And let's say we do this in 5.0 seconds. So we're going to have a change in time of 5 seconds. Typically, our starting time is 0. We typically start the timer at 0. So T2 is the amount of time that has gone by, 5 seconds. So the car went from here, traveled to here, traveled in the positive direction, that's important, and gained an appreciable amount of speed in 5 seconds. 30 meters per second is a little over 65 miles an hour. So, all right, we got some pep in this car. And the question might be, well, what was my average acceleration? The math's straightforward. We just plug it in. But I'm going to do something that's a little obnoxious. My average acceleration will be final speed minus initial speed. Well, my final speed is 30 meters a second, but I'm going to put a plus sign there to indicate that I'm moving in the positive direction. And this will become clear why I'm doing this later. Now, typically in math class, if a number is positive, you don't put any sign. I know that. And this positive sign isn't needed. But again, I want to make something very, very, very explicit. Now we're going to subtract the initial speed. Well, the initial speed was 0. We weren't moving. I don't even need 0.0, I just need 0. Fine. I'm going to divide that by the 5 seconds. So you will see that it's a positive 6.0 meters per second squared. This is important. My acceleration is positive because I am gaining velocity, speeding up, getting faster. So that positive is telling us something. Now I'm going to contrast that with another situation where the car isn't initially at rest, nor is it going to end up at rest. The car is going to have 2 different velocities at 2 different times. And that all depends, when you glance over and start observing the object in motion. So in the second example, that previous example was speeding up in the positive direction. Now I'm going to slow down in the positive direction. So my first speed I want to start off with, or velocity I should say, is 25 meters per second. And I am going to slow to 10.0 meters per second. So, you were traveling along the road, you're in the car, and you see that you're going to stop, or slow down, you're coming up to a traffic area, and you start pressing on the brakes gently, and you slow down from 25 meters a second to 10 meters a second. Now, there could be tons of motion before and after this analysis, right? This car could have been traveling at 25 meters per second up to this point. It could have been slowing down. It could have sped up. We don't know. We don't know. We don't care. The analysis for this particular problem doesn't look at that. And again, after the car has traveled and slowed down to 10 meters a second, things could still be happening. The car could still be slowing down. It could just glide in and stay at 10 meters a second. It could suddenly hit the gas again. We don't know. We don't know. Regardless, to find just this particular analysis, we put in the values. And again, I'm going to be obnoxious with these positive signs because I'm moving in the positive direction. These are positive velocities. So we go, final speed is 10 meters a second, minus the initial speed, which is 25 meters a second. And again, I'm going to throw that all over 5.0 seconds. Now, yes, this is going to just very easily it's a subtraction. The initial's larger than the final. And when that happens, you'll know you're going to get a negative answer. So 10 minus 25 is going to be minus 15 over 5. You've got an acceleration, an average acceleration of 3 meters per second squared. But negative. Negative. That negative's important. What's that negative telling you? You're slowing down. Your velocity is decreasing over time. Now, let's talk about what this means, whether it be a positive acceleration or a negative acceleration. This means that every second your speed is changing by that much. So that means you're at 25 meters a second at 0 seconds. After 1 second, you will have slowed down 3 meters a second. 3 meters per second it's changing. So after 1 second, you're down to 22 meters per second, because 25 minus 3 is 22. And then the next second, you'll be down to 19 meters a second, because 22 minus 3 is 19. And then subtract another 3 meters per second for the next second of travel. You get the gist. So you lose that much speed per second. 3 meters per second lost per second. Or in the other example, it will be so many meters per second gained per second. Now, we're doing average acceleration. But in this course, we're going to assume that that average acceleration is also nice and constant. Meaning, just like in the previous example, that 3 meters per second lost every second is nice and consistent throughout the motion. It's nice and uniform. You're slowing down in a uniform way, or in the previous example, you're speeding up in a uniform way. So a lot of this course assumes that average acceleration is also a constant acceleration for that motion. Now, in the real world, that's not always the case. In the real world, sometimes the speeding up or slowing down is not nice and consistent, not nice and constant. It's very, the term they use in physics is jerk, right? Because if you've ever been in a stick shift car, someone's just learning how to do stick shift, and they're trying to speed up, and they're shifting gears, they speed up really fast, and then they shift a gear, and you go, whoa, and then you kind of bounce around, and then they speed up again. So you're speeding up the entire time, but it's very jerky. Not to say that we won't have a little conversation about non-consistent or non-constant accelerations in this class, but most 95% of the accelerations in this class will be nice and smooth and constant. Okay. Now, I hope that all made sense. 2 more examples, and then we're going to take a break, and then we're going to get into graphing and showing acceleration via graphing. So that's going to be fun. Anyway, get ahead of myself. So let's change this up, and we're going to do speeding up in the negative direction. And so we're no longer over here. We're here. We're going to turn. I'm not redrawing the car, but we're going to turn the car around, and we're going to go this way. We're allowed to do that. We can drive backwards, turn the car around, go in the negative direction. And if we do that, we can still find acceleration. Sure we can. So this first example, I'm going to go, I gotta look at my little crib sheet here, sorry. We're gonna go 4 meters a second. To 6 meters a second. But since we are going this way, these are going to be negative velocities. If I'm calling that positive, but my object or my car or my person or whomever or whatever is moving backwards, those velocities, because this is change in velocity, are negatives, indicating you're moving backwards. That is key. And when I plug that into the average acceleration formula, it has a profound effect, because final minus initial velocity. So my final velocity is -6 minus my initial velocity, or I should put -6.0, sorry about that. My initial velocity is -4.0, but remember you're minusing a minus because it's a change in velocity. And I'm still going to say that these motions happen over 5 seconds. I'm going to keep that time consistent for these examples. If I do this, it's -6.0 plus 4.0 over 5.0, which, if you do the math, it's going to be -2 over 5. So I believe that comes out to -0.40 meters per second squared. Yeah, I mean, acceleration can be a small value. It doesn't have to be a whole number. It doesn't have to be large. It can vary. But what this negative says is that we are speeding up, but in a negative direction. We're gaining speed, gaining velocity. This way. So that was weird, because when we had a negative acceleration before, we were moving this way, but we were slowing down. Now we have a negative acceleration and we're moving this way, but we're speeding up. We're going to talk a little bit more about that soon. We're going to put those pieces together, but keep that in mind. The last piece is slowing down in the negative direction. And if I do this example, look at my crib sheet, I had some examples. We're going to start off at -18. And we're going to go down to -3 meters a second. For whatever reason, we were moving this direction. There was motion beforehand. Again, I don't know what was happening beforehand. We were moving this direction, and then, we were moving backwards at 18 meters a second. We're moving pretty fast, and we start slowing down for whatever. We hit the brakes, and we didn't quite stop yet, but we're still slowing down. And then eventually, after this position, do we keep slowing down? Do we stop? Do we keep moving constant? I don't know. We don't care. But between this 5-second time frame, we've slowed down from 18 meters a second to 3 meters a second, but backwards, negative direction. And of course, final minus initial, so -3.0 minus a -18.0 over that 5-second interval, because I'm keeping that 5-second interval. And it's going to be -3.0 plus 18.0 over 5.0. That's going to end up being positive 15 over 5. So that's going to be a positive 3.0 meters a second squared. So even though you are slowing down in the backwards or negative direction, it's a positive acceleration. Yeah. So 2 positive accelerations, when I'm speeding up in the positive direction or when I'm slowing down in the negative direction. 2 negative accelerations, when I'm slowing down in the positive direction or I'm speeding up in the negative direction. Interesting. So, like I said, we're going to put some of that together in a couple lessons from now. Talk about connecting this a little bit more. But before we do that, I want to talk about velocity time graphs and how we can determine some information from those. So, hang in there. We'll be right back.